we'll continue our lecture. We talk about, for the machine learning, talk about PCA to reduce the space dimension from higher dimension, and we'll reduce to lower dimension. And then we talk about LDA, and PCA is the unsupervised learning. The important thing is that like a face detection or face recognition, they are doing it from original face and then transfer to eigenface. Eigenface meaning the first dimension we call the first eigenvector. Okay, also called the first principal component. And probably that one, we call the importance or attention. Or pay attention on what? Okay, the important one is the eyes. And the second dimension, they will extract the important information about the mouse because compare all of the data, the eyes, everybody. So the variance is the maximum, the biggest. Everybody has different variance. And the mouse. So because they have a big variance or big difference, so it's easy for us to do the discrimination. Okay, but PCA, it does not do any discrimination. No, they just do like a clustering. They do the first dimension, second dimension, so it's a project to the other space. So the rest of the dimension are not important. So we just reduce the rest of the dimensions, so we can reduce the space. Okay, and then we start to do the discrimination, do the classification, and we'll use the LDA. So before we do LDA, we need to do the PCA. So both are combined together. Do PCA first, and then do LDA. But PCA is only one method for the important feature extraction. Okay, it's one method. There are different kind of we call it domain knowledge. So we can use different kind of method, not only PCA. Transfer to the new from original space, transfer to the new space, and then we do LDA for discrimination. Okay, so PCA basically and LDA basically, they are trying to do is reduce the dimension. PCA reduce more dimension. LDA probably just reduce. Suppose right now PCA reduce from 100 dimension or 1000 dimension, reduce to 10 dimension, and then LDA only reduces from 10 to 9, probably only one dimension. But the purpose for LDA is for discrimination or classification. And SVM is different. SVM is try to use kernel function we call activation function. They will project the data from original space based on the kernel function or activation function. They project to higher, we probably project to higher dimension, and then do the classification. So SVM and the PCA plus LDA are different. So we already talked about the PCA, and last week we mentioned a little bit about LDA, and today I try to finish the LDA. So I start again. So last time I told you, okay, if you try to, basically we try to find this line. The purpose for this line is try to separate or discriminate two clusters. There's two clusters. So the purpose is try to find the line. But however, we find if we try to find this line, because this line, each line consists of this W and x is the input data, is simple. So x is input data, we know. And w is the normal direction of this line. So last time we say, okay, w is parameters or normal direction of this line. And what's the physical meaning of w? That is rotation and scaling, right? Rotation and scaling to control the lines here. So control the rotation and scaling is big or small. So in our case, we don't need to consider scaling. So we only consider the rotation. And rotation actually is cosine, and the sine is an affine transform. Okay. So this equation is meaning a line here, and we have input sample x. So if a 2D will be x1, x2, w1, w2. If it's 3D, it's x1, x2, x3. Okay, w1, w2, w3. And what's w0? There's a translation. It's shift. It's meaning this line will shift along normal direction. Shift is meaning the distance from the origin to the line. This one represents the distance from the origin to the line. Okay. So that's entire physical meaning. So they have for each line, they have information of rotation, scaling, translation. So it's kind of an affine transform. So suppose we are doing the phase detection, and we have one cluster here, and the second cluster is here. So suppose the cross mark, is non-phase distribution. The circle is the phase distribution. So in the 2D, suppose in 2D, but if your phase is 20 by 20 pixels, that's meaning your space is 400 dimension. But here we just an easy way to say, suppose only 2 dimension is a x1, x2, and this is the position or location here and this here. How can we find a line here, the line L, to separate both clusters? Both clusters we want to separate. So that's meaning we try to find the normal direction L, because L control this line. So the LDA is try to find the W. After you find the W, and then you will know the line. Okay, so we start to talk about here. So this one, what I try to say right now is that because I don't know how to do this one. So suppose we have this one. This is suppose we are doing a Gaussian distribution. So this one is one cluster, and we represent by the Gaussian distribution. PCA is a model of Gaussian distribution. Okay, PCA is Gaussian model. The same LDA, the idea is a Gaussian model. So suppose 2D we have a Gaussian here, the other Gaussian here. We project to 1D, and you'll find there will be one distribution like this one. Okay, and the other distribution probably this way. So originally 2D, and we project to the W, and the Gaussian from 2D, or in the we call higher plane, higher dimension, you project to lower dimension. In the lower dimension, the distribution is still the Gaussian distribution. Okay, so that's meaning if we here we find a mean average value here, suppose average value is here, this average value is here, let's suppose. And so in the higher dimension, we have mean we have standard deviation for each cluster. We project to the lower dimension, we will find we have the other mean here and here. Okay. So later I will prove is that two way. Here, if you try to find in the 2D, you find the mean value, use the 2D. And after you project to the lower dimension, you find this mean. And both relationship is equal to, you just directly find this mean and project to the lower dimension. This average value project here. That's meaning you don't need to calculate it again here. 就是说你不需要在低解析度下再重新把每个 sample 都投影到低解析度再找mean，不用，你只要把这一点投影下来，这一点投影下来就好了。Okay, so what's LDA? LDA is meaning they have a concept. This is very important. The concept for LDA is important because didn't use that kind of concept. Didn't also use. So the best face recognition paper in deep learning, they use PCA. Deep learning model can use PCA, can use LDA. They also use kernel function. So see, in the machine learning, we do is PCA plus LDA, that's one method. For low dimension, no discrimination. We do SVM, higher dimensional discrimination. However, in the deep learning, they combine the kernel function that's related to the SVM. They combine the PCA, they combine the LDA concept. So the important one for LDA is a within and the between relationship. That's meaning we hope, because what we want to, our purpose is try to separate both distribution. You want to find a line or a plane to separate both distribution. That's meaning the mean M1, mean 1, mean 2 is as far away as possible. 你的目的是要找到这个 mean 以后，你要让 mean 1跟 mean 2分得越开越好。Okay, and then you want this distribute the standard deviation or variance as small as possible. So that's meaning if two distribution is this way, I use this one to draw. It's pretty easy. So if this is a projection line here. So if one distribution is this way, the second distribution is here. And this mean 1, mean 2. You want the overlap region as small as possible. You want to let the overlap region here as small as possible. That's meaning your case. We can do this way. Compare with the other one. That means this is better. And this is not good because they have an overlap region. What's the overlap region? It's meaning suppose we do face detection. Okay. And suppose this is non-face and the other is face. So they confuse. So you will make a lot of mistake. That's meaning your false positive will a lot. And this won't cause that will reduce the confusion region. So that's meaning you want to find a line that both higher dimension distribution project to the line, and then they can do as separate as possible. Okay, so that's meaning you want the mean 1 and mean 2 will be more far away. And standard deviation will be smaller. That's your purpose. So that's LDA. So in the exam, I will ask you, what's the major physical purpose, physical meaning of the purpose for the LDA? It's because the answer is that we want for the, we call this distribution we call the within. Between two distribution, we want between two distribution as far away as possible. And the other is within and between. Between two mean value. Within means each one, their standard deviation will as small as possible. Okay, so that's purpose. So back to here. So for the LDA, we have a two term we want to do. 我把它打字给你，就刚讲的。So we want between vs within， 是这样。Between meaning the average value M1, M2. So between meaning the average one, mean two will be as away as possible. Within is meaning standard deviation, log 1 and log 2, as small as possible. Each one individual, a small one, this one, smaller, 标准差越小越好，平均值越分开越好。And between also called this one, also called inter. Within also called intra. This you should know. So for the exam, I will do this one. I will ask you, the purpose for LDA actually is try to find the relationship between or within, or we also call inter or intra. Intra 是自己本身哦 ，inter 是我们两个之间 between 哦。So we want this one between as large as possible. This one will be maxima. This one will be minima. So that's purpose for LDA. So the purpose of this, we want to find a projection axis, actually projection line. Projection line is W. And then we hope this is theta. Okay, so that's purpose. So we back to here. We continue. Okay, so this one meaning we have two classes. Suppose is a phase and non-phase, or either one. And LDA also called Fisher's linear discriminant. 这个很有名哦，叫 Fisher， 这是一个应该是苏俄人的名字，姓 Fisher linear discrimination， 它是线性，它不是朗linear，它是线性的。好，那 Y suppose X is 2D, Y is 1D, so that's meaning if X, that's meaning you have X here. If you project to the W, it will become Y. So this axis, 1D axis, will be the Y dimension. Y domain, and the x1, x2 will be X domain. So each point you want to project to the W domain. Let's see here. So X inner projection. What's projection? Projection is a cosine theta. It's a relationship between two vectors. I say again. What's the physical meaning of inner product? Inner product is meaning you have vector v1 and v2. Okay, so suppose we have vector x and vector y. And you want to project from y, higher dimension, project to the lower dimension. That's inner product. Inner product is projection. Projection is a cosine theta. So here, the inner product becomes, so this is y. So it's 2D and it's 1D. Okay. So in 2D x, we try to find the average value n. Just 2D. And here, try to prove this 2D. Sorry, this 1D. 1D average actually equal to the 2D average value directly project to the 1D. 就是这里要证明是说你的2D 的那个平均值是 m 嘛，只要找到 W 的 projection 的 W 再投影下去，这个就是它的 1D 的平均值，要证明这一点。So here is this way. This is we try based on the average value of a 2D, we find a m, and 1D m headed equal to 2D any sample in 2D. If you W, we don't know W. W is the line you want to project. Actually, the normal direction you want to project. So after you project and get an average value, become in 1D average value. And 1D average value y equal to 2D average value project to W is this way. Because W is a constant term. So constant term we can move here. Okay, so finally we prove 2D average value can based on the rely on the W can project to 1D become 1D average value. So that's meaning in 1D you don't need to calculate y. You just calculate in 2D, calculate the average value m, and you can find W. Okay. So our purpose, I will go to here. So this is our purpose. Our purpose is try to, this is Jacobi value, just one constant value. We hope in the 1D, in the low dimension 1D, between two average value, the mean value will be bigger. For each standard deviation will be smaller. So that's what I mean here. We hope for the mean value will be bigger. So we can separate. For each standard deviation will be smaller. So that is this one. So if we can solve this equation, that's meaning we can solve W, and that's your final answer. 重点是你把这式子写出来了，那这个式子我们就要 maximize 这个式子哦。那这个式子找出来以后 ，W 就找出来了，答案就结束了，就这样。好，所以 modeling 是你自己要决定的。那这个观念在 deep learning 也是用这个观念。那重点是，deep learning 怎么写这个 deep learning 呢 ？deep learning 怎么跟 equation 产生关系？那我们实验室有做，在 face recognition 就有做这些动作。哦，你自己注意啊，我觉得你要往这边走才对。deep learning 它可以就是数学式子，像 affine transform。affine transform, deep learning has a model for affine transform. 那是军官在做的那个，警官在做，实验室警官在做这个，他做2年，都有产生一些好的结果。意思是说你一张影像如果是歪的，假设一 picture 进来是歪的 ，suppose it's face to face, right? You input this one. and you input to the face recognition or detection, you got a wrong answer. So if we have a small module, deep learning module, they can correct this one. If you input here, they'll correct to this one. No matter what kind of rotation, they'll do the correction to the normal direction, and then you can do the recognition. So deep learning is related to some equations. Okay, here we continue. So this is our purpose. So this is not good. So we try to continue formulate this one. So we have an n, right? N. So sorry, I should do this way. So our purpose is this equation. So first of all, we try to find average value. So average value is here, right? In the raw dimension 1D, our purpose is this one. We try to formulate this one. So m1 minus m2 square root equal to 2D. Which one is 2D? We call it square root. So 2D project to the 1D. 2D project to 1D. So this equation become this one. And we find SB is a between two average value. So this is our answer for the nominated term. 这是分子的 term。这个 term 我们推导成这个 term。那因为我们目的要求 W 是我们要求的值，所以我们就保留 W。那 n 已经有答案了，因为 n 就是2D 的那些点的平均值，所以 Sn we know Sn, we don't know W。那这是一个，所以刚刚那个式子，这个式子是我们要的，我们要求这个式子的最大值 maxima 的这个值。那这式子我们再把它经过刚刚的这个推导，分子推导，就变成这个式子，这是我们最后要求的。SB is known. Now, what's the standard deviation here? So standard deviation, this one, actually, 这你要看上一页这里，这里啊 ，standard deviation 在这里啊 ，2D, right? Each sample subject with the average value and square and do the average. So this is standard deviation. Okay. This one will become this between, and the denominator is here. 就这个。What's SW? SW equal to S1 plus S2. What's S1? That's individual. 那个 with 那个自己的 within 是每个自己的 standard deviation， 所以有 S1 跟 S2。那 S1 就是自己的那个 standard deviation， 就这个。自己 standard deviation， 那这个就是这个，就这个式子，那就这边好，那这样就可以形成这个式子。So we know SB, we know SW, we want to maximize this value, Jacobian, and so we try to find W. So how can we find W? So because we try to find W, so we the reference to the derivative to the W， 我们就对 W 做微分，那就变成这个式子。那二次微分式子的公式我帮你写在这里。二次微分，就分子分母的微分，我把它写公式帮你写在这里。So this one can formulate this one, and you'll find out this term equal to this term. This term actually equal to this term, and this term is a constant term. So we assume this constant term to be lambda, a constant term to be lambda. So this equal to lambda times SW times omega equal to SB times omega. And we move the non-term input term to shift SW here. So this input term is lambda. So we'll find out this one can solve by singular value decomposition. 这是我在教你们最佳化。When I teach you the optimization, right? We have several methods. Pseudo inverse, right? Cross and pseudo inverse and cross loop, sorry, the cross solution. If ax equal to b equal to 0, right? Ax equal to b equal to 0, and we use cross form solution. If ax equal to b doesn't equal to 0, we use pseudo inverse. There's two methods. The other one is this one. Sometimes we try to solve the solution, we find out become this term. This term is what? This term is the lambda times w is unknown, equal to a times unknown. The purpose is we try to find the maximum value of lambda. Sometimes we try to find minimum value of lambda. So in this situation, we can use SVD to do that. So W equal to eigenvector, lambda equal to eigenvalue。这要注意，我刚刚已经讲两个解法，没有，就只有这第三种，就只有这样子。我帮你整理过了，就只有这样，就只有这几种解法而已。只是一阶的 approach， 所以这个就变成 eigenspace format。So we try to find maximum value, but sometimes, some cases try to find minimum value of lambda equal to W. We don't know. So this is the eigenvector equal to this one is a matrix. You know the input matrix, and this is eigenvector again. So after we have this format, we can solve W using based on the A matrix using singular value decomposition. So you have a lot of eigenvector corresponding to eigenvalue. And then if you try to find the maximum value, so that's meaning your maximum eigenvalue corresponding to that vector is your answer. If you try to find the minimum lambda, it's meaning the minimum eigenvalue correspond to the eigenvector, that's your answer. So that's your answer. 这解完了。So you can solve W, omega, sorry. So that's your answer. So after you solve W, you can find the best normal direction. You can find best one. So this normal direction will corresponding to the line here. 意思说你要找 discrimination 那条线，你不能找线，你要找它的 normal direction。找到 normal direction 就是你答案就找到了。它不管 translation 跟 translation 没什么关系，因为 translation 只是这条线在这条沿着 W 在移动而已啊。这条 L 的线是沿着 W， 你 W 只要角度找到了，这条线是沿着 W 这样在移动。translation 所以重点在找 W omega。那这是 LDA， 这 LDA 忽然之间就结束了。那我讲这边就讲了。等下最后跟你讲说，像这个 distribution， 它 W 找到了，那 W 这个 eigenvector 是这个，那它的垂直线是 就 L 这样子。好 ，so that's for the SVM， sorry for the LDA， 就到这边。按错。